Hello, everyone. My name is Veljko, and I will be there as a tech support during the workshop. I want to introduce you to Abdelghani Kabot. I hope I pronounced that right. He's an NVIDIA DL instructor and ambassador at NVIDIA, and today he will be holding the fundamentals of deep learning workshop. So I hope everyone have a great time, and I give the word to you, Kabot.
Yeah, thank you so much for the introduction. Thank you so much for the invitation. Thank you so much for the Data Scientist Conference support. Everyone here, welcome to the Fundamentals of Deep Learning course hosted by NVIDIA DLI Institute. Also with the Data Science Conference at Belgrade, Serbia. Thank you so much again for the invitation. I'm thrilled to be your instructor today about the world of deep learning. Let's embark this adventure together, exploring the wonders of artificial intelligence and machine learning. Our course today is not just about learning, it's all about experiencing the transformative power of deep learning technology. First and foremost, I would like to extend a warm welcome to each one of you. As he said, I am Abdelghani Kabot from Algeria, North Africa. And it's my honor to serve you, to serve as your NVIDIA DLI instructor today. Data scientist, I think that data scientist conference, it's really amazing. And it's an opportunity for me to teach some of you. And I'm sure that I will learn so much from you and from your interactive questions, and also some additional information you have. I'm delighted to see that such a group of participants today interested in learning deep learning technologies. Before we dive into the heart of our workshop, I would kindly ask those who haven't done so already to create an NVIDIA account. You can do this by following the link of courses.nvidia.com/join. Please go ahead and create your account if you don't yet. Once your account is set, please visit to this link. Let me just copy it. Here is in the chat, courses.nvidia.com/DLI event. And then pass this code. Give me a second, please. Pass this code event. All of them capital letters. So when you create your account, then go to the DLI event link, course.nvidia.com/DLI event, and then pass the event code. Good. Please say yes in the chat if you're done. Please, can you give me an introduction about yourself, please, in the chat? Your specialty, your level, your university. So just that I can know how the level the audience is. Please, my voice is clear. Good. So everybody have now the course, the access to the course. Good. Sorry for that. Sorry for the connection. I lost my connection. Please, I will just go share my screen. I think now you see my screen now.
Yes, we can see.
Yeah. When you enter the code, it will let you to the page like this one. So you should click here, start here. At this point, please refrain from clicking further until I instruct it. Please don't click anything anymore. You will see this course, and then after an hour we will click to start your environment. Let me just go ahead to our first part. Today, I promise to be a journey full of learning, exploration, and most importantly, it will be really fun for me and for you. It's going to be a long day. I assure you it will be enjoyable and enriching for both you and me. So get comfortable, grab a bottle of water, and if you are coffee drinking, have your cup ready. I need you all energized, focused, and ready to absorb the fascinating world of deep learning that lies ahead. So to the first part, as I said before, welcome again everyone to the first segment of our deep learning journey. I'm thrilled to guide you into the dynamic world of deep learning. This class is designed to accelerate your understanding and skills in deep learning. It's not just about. It's not like it's not that kind of course you will learn how to code with CUDA. No, it's not like it's not that kind of course. Or something that you will learn some backend skills or software engineering skills now. It's just it will be your introduction to the fascinating world of deep learning. So we will focus on hands-on exercises to kickstart your own deep learning projects. Our aim is to our aim is to help you with the initial path to start your deep learning journey and get comfortable with today you will hear a lot of concepts, and if you understand them very well, after that you can learn anything and get to read any book or any paper on deep learning. So as I said, today we will keep you with the knowledge and confidence to delve deeper into the subject. So after that, as I said, you will follow some online courses or something, books, articles, papers. Also, there are some notebooks that are really full of knowledge, full of resource that you can follow them furthermore. They are really rich. So, all right, let's dive into what we have planned for today. Our journey through deep learning is structured into 6 distinct yet interconnected parts. Think of it as a series of acts in play, each revealing more about the fascinating world of neural network and deep learning. So first act or first part, it will be an introduction to deep learning. We start at the very beginning, setting the stage for what deep learning is all about. This is our intro to intro, primer to get everyone on the same page. Next, we will row up with our sleeves for our first hands-on exercise. We will be diving into the classic problem of recognizing handwriting digits, a perfect starting point for practical deep learning. Second act will be the mechanics of training neural networks, or how neural networks train. This is one of the famous models or algorithms of deep learning. Here we will delve into how neural networks learn from data. It's not just about feeding data into a system. It's an art and science of training these networks to make sense of that data. Third act, or the third part, it's the world of convolutional neural network, CNN. And now I am not talking about the news channel. It's CNN. It means that for deep learning scientists or for deep learning students means that convolutional neural network. So we will explore CNN's specific architecture of neural networks that's particularly good at handling images. I consider CNN is one of the really amazing patent in the world of artificial intelligence, and you will see why I find CNN so amazing from different angles. Third act, it's data augmentation and deployment. Here you will learn a neat trick here, how to use the data you already have to create new training materials or to new training data. We have a hands-on lab ready for you to try this. Then the fifth act, it's all about pre-trained models. Sometimes you don't need to start from scratch. You can use some pre-trained models, and we explore how to use pre-trained models in hands-on labs. And then in the sixth act, or the part 6, we'll move on to some more advanced neural network architecture like RNN, CNN, autoencoders, GANs, reinforcement learning, adding extra layers of sophistication to our learning. And finally, after this act, we will wrap up with an assessment. If you complete it successfully, you will earn your NVIDIA certification and a badge of honor showing your newfound prowess in deep learning. We can get into the first chapter of our deep learning adventure today. We embark on a journey that will take us through the history of AI, the deep learning revolution, and application of this transformative technology. And then we will start our first hands-on exercise about handwriting digits recognition. Just give me 1 second. So remember, so just I got a message. I'm always saying that we participants or me should to have fun in their learning journey. Remember that the essence of this workshop is exploration and enjoyment. Keep comfortable, stay engaged, and most importantly, have fun with the training. I'm here to help you with your questions, and please make the chat interactive with your friends or your colleagues here. So interact with each other and learn from each other. It's the day off. So please don't hesitate to ask your questions, no matter how small they may seem for you. We are all here to learn from each other, and every question is an opportunity to collective growth. With our slides as our guide, and in spite of curiosity, let's begin the existing journey into the world of deep learning. So now let's ponder over the fascinating differences in how humans and machines learn. It's comparison that not only reveals the uniqueness of our own cognitive process, but also sheds light on the design principles behind machine learning systems. When we talk about machine learning, especially in the context of deep learning, there are two critical phases: training and prediction. In the training phase, we feed data into a machine like a computer and teach it to recognize patterns and make connections. This is where the learning happens for the machine. Once trained, the machine then moves to the prediction phase, where it applies what it has learned to new, or what we mean by new, it's like the unseen data, unseen inputs, the data that have never seen it during the training. The key here is that the machine's prediction is based on the pattern it has learned during training. It's a process of expectation setting and pattern matching. Humans, on the other hand, have a more nuanced and multifaceted approach to learn. Our process is often described as rest and digest. We absorb information, take time to process it, sometimes stepping away and then come back to it with a fresh perspective. Our brains are not just pattern recognition machines. They are also adept to context understanding, emotional processing, and intuitive reasoning. When faced with a situation, our response can range from calculated decision, similar to the prediction phase in machines, to an instinctive reaction akin to the fight or flight response. This shows the complexity and adaptability of human learning. And honestly, the comparison with the human learning is what inspired and continues to inspire scientists in the design of artificial neural networks. The goal is to create machines that can, to some extent, mimic the reasoning of the human brain. While we are not there yet, the parallels and difference between human and machine learning offer rich ground for exploration and advancement in the field of AI and deep learning. So as we delve deeper into neural networks and machine learning, keep the comparison in mind. It will help us appreciate not only how far we have come in developing intelligent systems, but also how they differ fundamentally from our own incredibly complex brains. Let's go to the history of AI. As we delve into the world of deep learning, it's crucial to understand the roots of artificial intelligence. The history of AI is not just a timeline of technological advancement. It's a story of human ambition, evolving dreams, and the relentless pursuit of mimicking human intelligence. In the early days of computing, the primary goal was straightforward: to create machines that could perform tasks typically done by humans. These tasks, however, were relatively simple and rule-based. For instance, think of early computers that were designed to calculate complex mathematical formula or equations, something that was laborious and time-consuming for humans. These initial steps, while impressive, were not really what we would call AI today. They were more about automation and efficiency rather than intelligence. As the field progressed, there was a surge of optimism. Many believed that achieving human-level intelligence through compute, or what we call by human-level intelligence, is artificial general intelligence, AGI. As I said, many believe that achieving human levels intelligence through computer was just around the corner. This period was marked by grand prediction and ambitious goals. Researchers and the public alike were fascinated by the possibility of creating machines that could think, learn, and reason like a human. However, as time went on, it became evident that generalized human intelligence, or AGI, was a far more complex goal than initially anticipated. The challenge is creating machines that could understand context, process natural language, and learn from unstructured data were immense. It wasn't just about programming more rules. It was about enabling machines to learn and adapt Fast forward to today, and the landscape has dramatically changed with the advent of advanced machine learning techniques, especially deep learning. We are now witnessing systems that exhibit traits early reminiscent of human intelligence. This is not the general intelligence of science fiction yet, but it's significant leap from the rule-based system of the early computing era. So as we explore deep learning further, keep in mind this rich history. It's a history that shows us both the incredible progress we have made and the ambitious path that lies ahead in our quest to understand and replicate the marvel that is human intelligence. So early neural network. Let's turn back the clock to the 1915 to the dawn of neural network. The concept of early NNN or neural network was heavily inspired by our understanding of biology, particularly the structure of and function of the human brain. It's fascinating to think that the quest to replicate the working of our own neurons kick-started this journey. Not longer after computers came into existence, visionaries began experimenting with artificial neural network. They envisioned creating computer systems that could learn and adapt much like a human brain. This was a bold and ambitious idea, especially considering the technological limitation of the time. There were some notable success here. This early neural network showed promise in tasks like reading handwriting digits and even playing games like maybe you heard backgammon. However, this success didn't quite herald a revolution. The computational power available at the time was a significant bottleneck. Training these networks was immensely time-consuming task. Just imagine trying to train a network with computing resource from 4 decades ago. It's really hard and time-consuming. During the period, another computing paradigm was gaining ground, the von Neumann architecture, named after the New York mathematician and physicist John von Neumann. This architecture became the foundation of modern CPUs and outperformed early neural network in many tasks. It was a more practical and efficient approach given the technology of the era. For those interested, there are included in the slides some resources to dive deep into the history of early neural networks and the von Neumann architecture. You find here some really good results, good resources for that. As we proceed with today's session, keep this historical insights in mind. They highlight not just the ambitious beginning of neural networks, but also the incredible journey of technological evolution that brings us to sophisticated systems we will be exploring in our hands-on labs. As we explore the landscape of early AI, it's important to discuss expert systems, a significant approach that dominated the field before the rise of modern neural networks. Expert systems are AI programs that mimic the decision-making ability of a human expert. Essentially, they are complex rule-based systems that use a set of if-then statements to solve a specific problem in a narrow domain. Let's give an example. If you wanted to create a medical expert system, here you will involve several detailed steps, from defining the problem domain to designing the rule-based logic and testing the system. First of all, you start by defining the problem domain. Identify the specific area of medicine the expert system will address, like diagnosing cardiovascular disease, CVDs, or pathologies, or radiologies, or cancer disease. First of all, define the domain area. And then you should go to medical expert or consult the medical expert to understand the decision-making process in this domain. Then after that, you start to the phase 2, knowledge acquisition. Here you should gather the detailed knowledge from a human expert like doctors or specialists about diagnosing and treating a condition with the chosen domain. So this process can include interviews with the specialist, with the expert, observations, and studying medical literature. Here you should to be also familiar with the concept of medicine. Then after that, we start to define the knowledge base. Here we develop a big database that contains all the relevant medical knowledge for the system. This includes the symptoms, diseases, treatments, patient histories, and etc. The knowledge base should be structured so that it can be easily queried and updated. Then we start with the hardest, the really hardest phase, which is the developing the inference engine. This is the core of the expert system, where the reasoning and decision making happen. The inference engine uses if-then-else statements to draw a conclusion from the knowledge base. For instance, for example, if symptom A and symptom B are present, then consider diagnosis X, for example. If symptom B and A and C are present, consider diagnoses like Y or Y, sorry. Sometimes we should also implement in fuzzy logic because it can help handle uncertainties and variabilities in symptoms and diagnoses. But building such system is a colossal task. It requires hundreds of engineers and programmers to do this. If-then-else statements, covering as many scenarios as possible. However, despite this complexity, expert systems have significant limitation. One major drawback is their lack of flexibility. If an expert system encounters a scenario that is not explicitly programmed into its database, it struggles to provide accurate or meaningful output. This is often summarized as garbage in, garbage out. If the input or the scenario isn't anticipated by the system rules, the output will be ineradicable. Moreover, these systems lack the generalization capabilities of modern AI systems. They are excellent in their specific domain, but cannot adapt or learn beyond their programmed rules. Rigidity contrasts starkly with the more dynamic and adaptive nature of neural networks, which we'll explore in our hands-on labs. Neural networks, especially with deep learning, can learn from data, adapt to new scenarios, and provide insights even in case not explicitly programmed into their architecture. So as we move forward, keep in mind the evolution from this early expert systems to the more flexible and powerful AI technologies we have today. It's really a journey from rigid rule-based logic to adaptive learning-based systems. Let's take a moment to look at these three images we have here. Towering wave, cute kitten, and the vintage car. These images provide perfect illustration of the inherent limitation of expert systems. Consider the challenge of programming an expert system to recognize this object. How would you go about extracting and defining the rule that could enable a computer to identify a big wave, a kitty cat, or an owlet car? Write in the chat how you can do this, and I will be back to see your answers. It quickly becomes apparent that distilling this visual concept into rigid programmable rules is an incredibly complex task. Expert systems operate strictly within the boundaries of human-defined rules. They can only process and respond based on what programmers have explicitly coded into them. This means the effectiveness of an expert system is directly tied to the extent of human understanding and the ability to convert this understanding into concrete code. For certain well-defined tasks like routing customer calls to sales, this is really an example of where expert system works well. Routing customer calls to sales representative based on region and industry vertical. Expert system perform very well here. The rules are clear, specific, and relatively straightforward to program. However, when it comes to tasks that humans find intuitively easy, like recognizing objects in images, the limitations of expert systems become starkly evident. Take a moment to think about how you effortlessly recognized the object in these pictures. For most humans, identifying a cat, a car, or the ocean is almost and sometimes really requires little conscious thought. But how would you explain this process to newborn child, or more pertinently to a computer? It will be difficult to show a newborn child how can recognize this object. The intuitive leap we make in recognition is incredibly difficult to replicate in a rule-based system. This discussion underscores the need for more advanced forms of AI, ones that can learn from data, recognize patterns, and make decisions in ways that mimic human intuition and perception. It sets the stage for our exploration of neural networks and deep learning, which represent a significant leap beyond the capabilities of traditional expert systems. In examining how children learn, we gain valuable insights into the principles of deep learning. Just like a child, deep learning algorithms require exposure to vast amount of data and the correct answers for this data. Think about it. When we teach children, we don't just give them rules, we expose them to examples. We show them objects, name them, and they over time begin to identify patterns and make connections. This process is strikingly similar to how we train deep learning models. Consider trial and error. Fundamental technique in both child learning and deep learning. When a child is learning something new, they make predictions, test them, and learn from the outcomes. Whether they are right or wrong, deep learning models function similarly. They make predictions based on the data they have been trained on, and through continuous adjustment and learning from errors, they gradually improve and become more accurate. So as we delve into deep learning, imagine it as teaching a child. We are not programming strict rules. We are guiding a learning process, one that is dynamic, adaptive, and in many ways inspired by our very own learning methods as a human. Deep learning revolution. So there was a time, particularly through 1990s and early 2000s, when the dream of powerful AI seemed quite distant. Neural networks were in the use, but they weren't achieving groundbreaking results. However, two major developments converged to kickstart what we now call the deep learning revolution. These were crucial in transforming the landscape of AI and bringing us to where we are today. As we pivot to the role of data in the deep learning revolution, let's consider the scale. Neural networks need a rich tapestry of information to learn effectively. In the slide, we see a visual representation of data growth, a metaphor for the explosion of information in the digital era. The internet has been the great enabler, providing deluge of data for neural networks to feast upon. Imagine trying to teach neural networks to recognize a cat. It's not just about showing it a few images. The networks need to see thousands of cats in different poses, lighting, and context, alongside countless images of not cats, the opposite class. To understand the essence of catness, it's this scale of data that has fueled deeper learning capacity to learn and generalize. So we need big data, a big amount of data, and not just a big amount. We need also a variety of data so that it can learn very well. Moving to our second enabler of the deep learning revolution, computing power. This image of a camera in hand symbolizes observation, critical function of learning. For an artificial brain to observe and learn from the vast amounts of data available, it needs immense computing power. Let's put it in human terms. Consider the incredible amount of information our brain processes every second. The high resolution, high frame rate experience of life, our AI systems strive to match this, and it's here that computing power comes into play. It's not just about having the data, it's about processing it swiftly and effectively, making observations and learning from them with a practical time frame. While AI might not match the human brain's processing capacity, advancements in computing power have significantly narrowed the gap, enabling the marvels of deep learning we see today. As we delve into the engines behind AI rapid acceleration, we cannot overlook the GPU, the graphics processing unit. This powerhouse of computing has been the catalyst in our ability to excel at AI, train intricate neural networks, and bring numerous applications into production. The revolution brought about by GPUs hinges on surprising similarity between computer graphics and neural networks operation. Both require heavy lifting in the realm of mathematics, specifically linear algebra and matrix multiplication. To chain an image, we mean by chain to transform it into a format that neural networks can understand and use. To chain an image is to represent it as matrix. This is akin to the way we perform operations within a neural network. On the left, we have computer rendering of marble. This visual magic is achieved by manipulation matrices that represent the marble's geometry and surface properties. On the right, we have an abstraction of neural network, which beneath its complex structures is fundamentally a series of multiplications. Neural networks, much like computer graphics, are built on bedrock of matrix operations. They transform and manipulate data through layers and computation, much like how computer graphics transform and rotate countless tiny triangles to create seamless image. The parallel process, or GPU, emerges as a hero in this narrative. The calculations needed to train a neural network are vast and repetitive, requiring simultaneous processing to be efficient. While a typical CPU may have a handful of cores capable of parallel processing, a modern GPU has thousands of cores, making it parallel processing titan. The GPU and the machines you are using today for this course has thousands of these cores. They are not just well suited for deep learning tasks. NVIDIA has fine-tuned them to be specifically architected for training neural networks. And this is why NVIDIA is really what NVIDIA is doing. It's really impressive and really amazing. NVIDIA has, as I said, it helps us to train these neural networks very easy. This is why GPUs are not just an add-on on AI research or just a plus. They are fundamental piece of the puzzle that enables us to push the boundaries of what's possible. Because before GPUs, neural networks has stopped for long time, and then come back when the GPUs become more powerful, or the computing becomes more powerful. So what's deep learning? Deep learning is the revolution approach that redefines the essence of programming. Rather than explicitly coding every rule into a system, deep learning enables us to build algorithms that learn from data. It's a fundamental shift, turning traditional programming on its head. Instead of telling a computer how to solve problems, we are now teaching it to figure out solutions on its own by recognizing complex patterns and making intelligent decisions. As I said, deep learning flips the traditional programming on its head. So let's contrast this with traditional programming, where everything operates on finite sets of defined rules. Think back to the expert systems we touched upon. We extracted rules from human experts and translated them into code. In this world, programming is about setting concrete parameters and classification, feeding examples into a system and relying on it to make decisions based on those predefined rules. It's a process that's clear-cut, but lacks the ability to adapt beyond that what's been explicitly programmed. Machine learning, on the other hand, flips the script. Instead of starting with rules, we start with labeled examples, or what we called the supervised learning. This method doesn't really own us knowing the rules beforehand. We allow the model to make predictions, give it feedback, and thrive this iterative process involving thousands, even millions of guesses. The model learns its dynamic process where the system establishes its own rules, learning to categorize or predict based on the data it's been trained on. What sets deep learning apart of its ability to discern these rules autonomously without needing them to be hard-coded by humans, it's not just learning, it's learning how to learn, which is the crux of the deep learning revolution. So when you choose deep learning and when you not choose it. And the diverse landscape of programming, the choice between classic programming and deep learning hinges on the nature of the problem we are tackling. If the rules are clear-cut and straightforward, classic programming might be the way to go. It's like following a well-drawn map, simple and direct. However, the world is rarely so black and white, When we step into real fields with nuances, where complexity reigns and rules are not just difficult to define, but are ever changing. That's where deep learning changes. Consider tasks like recognizing the subtitles of human speech, identifying objects, or detecting anomalies that don't follow any fixed pattern. In this case, the intricate layer learning approach of deep learning is unparalleled. Geoffrey Hinton, pioneer in the field, famously said, deep learning is going to be able to do everything. And indeed, the potential seems boundless, but with great power comes great responsibility. As we integrate deep learning into more aspects of technology and society, we must also navigate the ethical implications, transparency, bias, and privacy. There are just few of the consideration we must address as we advance with this powerful tool at our disposal. Deep learning compared to other AI. Deep learning is just one approach, one branch of the expensive tree that is artificial intelligence. But it's a branch that's growing rapidly and bearing fruit in many fields. Now why do we call it deep? The deep in deep learning isn't just a buzzword. It refers to the multiple layers, times hundreds, that make up neural networks. These layers are where the learning happens, where data is transformed and abstracted into higher level features. It's in this depth that complex rules, which are often beyond explicit definition, are designed by the model itself. Imagine trying to codify the laws of physics for simulation from scratch. It's really a Herculean task. Yet, a deep neural network can be exposed to various physical systems under different conditions, and it can learn to predict the physical responses without us having to program the rules directly. This capacity for learning and abstraction is what sets deep learning apart from traditional machine learning. While traditional models might have a handful of parameters, deep learning models can have billions. These parameters are part of what we call hidden layers, and they are pivotal for tasks that require deep understanding, like natural language processing, which powers translation services, text generation, like ChatGPT, and more. So when we are faced with exceptionally complex tasks where the rules are as fast as the stars in the sky, that's where deep learning models excel. They don't just learn; they learn to understand, and is doing so. Take us one step closer to AI that can truly simulate the depth and nuance of human intelligence. Deep learning isn't just scientific curiosity. It's driving force for innovation. In countless fields, you have likely heard about or even interacted with technologies that have been revolutionized by deep learning. From the way we communicate to the products we buy, deep learning is quietly and consciously redefining the realm of possibility. In the domain of computer vision or CV, deep learning has been a game changer. It's not just about teaching robots to recognize objects. Stuff that's centrally impressive. It's about the nuanced tasks like object detection, which involves location, items within an image, and segmentation also, which is about partitioning an image into segments to identify and isolate different elements. The difference between detection and segmentation is subtle but crucial. Detection is about identifying the presence of object, while segmentation involves precisely outlining and differentiating those objects. I don't know if I can show you the object. Sorry, I should open Google. For those who don't know what we mean by object detection and segmentation, as you, it's like locate the object, but here we segment the image into segments. So and then there are the automotive industry self-driving cars, like those developed by Tesla or BMW. Tesla have leveraged NVIDIA GPUs for years, both in vehicles and in the development of their custom chips. These applications represent just the tip of the iceberg in computer vision potentials. Natural language processing, or NLP. We are engaging with deep learning every time we ask Siri or Alexa to play our favorite song. Large language models, LLMs like ChatGPT or like Falcon or like Jace or like Mistral, or like Zephyr. There are many other LLMs. These LLMs are advancing the field further, enabling real-time translation and voice recognition. Yes, even if your voice is hoarse or you are sick because you are under the weather, or the model will recognize your voice very well. Also, virtual assistants are becoming more adept, handling tasks via speech or text, and understanding complex instructions. Notable projects include Google's BERT, which has transformed search algorithms, and OpenAI GPT series, which has pushed the boundaries of generative text. Also, recommender systems have transformed retail and online shopping. Imagine you are browsing Target website. The items you see are created to align with your interests, thanks to deep learning algorithms. This system analyzes your behavior, along with data from millions of other customers, to predict what you might want to purchase next. If you ever noticed how after shopping for a car, for example, for a car online, you suddenly start seeing ads for cars elsewhere. That's a recommender system in action. For example, Amazon's customers who bought this item also bought future feature is a classic example of recommender system at work, making shopping experience both personal and intuitive. Reinforcement learning, or RL, is another AI frontier where neural networks have made significant strides. Maybe you have heard about RLHF, reinforcement learning human feedback, and this is where GPT-3, GPT-4 trained with transformers. As I said, this RL have made significant strides by reinforcing the positive behaviors to achieve a goal. Reinforcement learning has been pivotal in game playing AI. Maybe you have heard about AlphaGo. AlphaGo over the world of Go champion and AI bots. You know, maybe that you heard that AlphaGo beats the world champion in Go. Also, professional video game. Also, AI bots outperforming professional video gamers. In the financial world, trading algorithms powered by reinforcement learning can execute trades faster than any human, showcasing the speed and efficiency of AI-driven decision making. This advance demonstrates how training AI can happen at astonishing speeds, with learning and adaptation occurring in real time. So, as we prepare to delve into the course content, remember that hands-on exercises are at the heart of this experience. They are designed to make you comfortable with deep learning workflow. We expose you to a variety of models and datasets, and you will have the opportunity to take the notebooks and slides for personal use. Also, they are just for you, so please keep them confidential. Don't share them with anyone, please. Because you know that this course is not for free, but we give it to you for free. Usually it costs us $500 for each one, but we give it to you for free because you are still students. So please don't share this with anyone. we are about to take I think that we should to take short break from the slides. So please go ahead to this page and click to start or start. It will take some time to load our environment. So please go ahead and click to start. So you will see now loading spinner indicating that the cloud environment is preparing your remote workspace with all the course content. This will take a few minutes, but in the meantime, let's continue with the slides. So So sorry.
Welcome back.
I lost my connection. So just I check if there is anything in the chat. So as I said, please go ahead and click on start. I don't know if you hear me when I say this.
Can you just share your screen?
Yeah, I'm going to share.
Okay.
So please go. I think that I saw. I don't know where I am, where I lost my connection. I think that I said this. Click to here to start. Please, everybody can do this. You start to see here the slides. Let me get back to the structure of our course. As I said, the course is structured to build your deep learning skills progressively. We'll start with a hello world of deep learning and an introductory program to get you started. Then we will move on to train in more complex neural networks. We explore new architectures and techniques to enhance performance, and we will discuss how to leverage pre-trained models and also transfer learning, which is method that allow us to apply knowledge from one domain to another domain, which is not just effective but also incredibly fun to work with. We will also try to do text generation with LST and long short-term memory. And then finally, we will have the assessment that you will pass very quickly. It's really easy, and then you can have your NVIDIA certificate if you pass successfully in the time. So as I said, it will be a long day, but it will be really with a lot of fun and a lot of interactive with each other. The platform of the course, the platform powering our course today is GPU accelerated cloud server running. Jupyter Lab, if you are familiar with Google Colab, you will find Jupyter Lab there. New to it, don't worry, it's user-friendly and highly interactive. Jupyter Notebooks allow you to run Python code and see results directly within the same interface, much like a digital lab book that's both readable and executable. Software. Many of you may already be quite popular deep learning frameworks like TensorFlow, Keras, as well Torch, MixNet, and JAX, the new framework of Google. In our sessions, we will be focusing on TensorFlow and Keras for their accessibility and robustness. These tools are the industry standard for developing and deploying deep learning applications, and they will be instrumental in your learning journey throughout this course. So the first exercise will be classify handwriting digits. This will be our first hands-on exercise. It's classical one, classifying handwriting digits. Imagine the complexity of this task for traditional computing. In the past, expert systems or computer vision techniques might have approached this with statistical image analysis. Daunting task indeed, but then came the realization that neural networks could excel at recognizing patterns in writing text, be it digits or letters. The beauty of neural networks lies in their ability to learn the nuances of handwriting digits without explicit rules about shapes or strokes. It simplifies what was once a formidable challenge into something quite manageable. Let me now go to the lab. So if you see here, try to click to launch. Launch will open our Jupyter Lab platform. It's similar to, as I said, it's similar to Google Colab. So just to explain this, there are lunch task, stop, and ACES task. ACES task is for quizzes. Don't click to this. When you finish the assessment, we will back here and click to ACES task to get your certificate. And then we will have stop. It will end our GPU session, and lunch. It will launch our environment. So here I have Jupyter Lab. Let's open the 00. As I said, Jupyter notebooks can include text, graphics, and executable codes, cells. To run the code, there are some codes here. Please see here. To run the code, there are two ways. Sorry, there are two ways here. You can either click the run button, just put the mouse here, and click to the run button here. This is the triangle one. It will execute it and see the result. Or my personal favorite way, it's by using the keyboard. Put the mouse there, and click to Shift plus Enter, Shift Enter together. Here you see it. You can even go to the next cells by Shift Enter. Shift Enter, it will go to the next cells. So one critical thing to note: at the end of the notebook, there is step to clear the GPU memory. This is important to ensure you don't carry over any unnecessary data into the next part of the course. So please always remember to execute the memory clearing cell at the end of each lab. Don't forget, please don't forget this. And if you forget it, please go to here to kernel from the menu kernel. Shut down all kernels. The one that's at the end. Shut down all kernels, click on it, and then click on shut down all kernel. Here you see on the right, there is no kernel. So please click on it, no kernel, and then select the Python 3 kernel. Here it will be clearing all the memory you have. And then you should to start your notebook from the beginning. So go ahead to the first exercise. You will be working with the MNIST dataset, foundational dataset in machine learning that contains thousands of handwriting digits. I will walk you after you through the first few steps, but first I want to give you some time to explore on your own. Please read through the notebook, run the code, cells, and familiarize yourself with the environment. With that, I will stop sharing my screen and give you about 15 minutes to dive in. Don't hesitate to reach out if you have questions. So enjoy your exploration. You see here. Yeah. It takes way too much time to run just being safe. No, maybe just because it's your internet connection. It's not. Here you have Tesla T4 with 16 giga of VRAM. So it's more powerful than Google Colab. So go ahead and enjoy the first exercise. I will give you, as I said, 15 minutes, and then I will back after that. In the meantime, if you have any questions, you can write them in the chat. Hopefully that the first part was clear. Mm, P Jack, maybe you have some problem. Please try to go to kernels from the menu, kernels, and shut down all kernels. And then set the Python kernel, Python 3 kernel, and then execute it again and see. If it doesn't work, please share your screen and I will help you. Please, others, can you give me 1 second to introduce yourself, please? I have asked this question before. So, what's your level, your specialty, your university, your country? I think that there are a lot from Europe, not only from Serbia, I think. Yes, please write in the chat. Jack, can you please share your screen? Good. Sorry, I can't read Bulgarian language. I don't know what's your name, but I am the student of 4th year of faculty. Good. Happy to know you. Please, the others, go ahead. Okay. I think that you are right. You haven't the option to share your screen. So please go ahead. Go to the lunch page where we start. Where we start. Where we start, and click to stop. On stop, and then restart again and see. If this doesn't work, please change your browser. Maybe it's because your browser.